Welcome back, people. I hope things are going fine. Before delving into the new week, let's do a little bit of a recap where we are. We have dynamics in the sense that we might have systems of the type y dot a vector equals to f y and potentially other variables. This is vectors in the sense that we might have, for example, lotka volterra, preys, predators, and the derivative on the preys or derivative on the predators. We have graphical interpretations of functions defined over the domain that give us time derivatives. If I tell you that I have a point here that is the same point here, for which this is positive and this is negative, at this point, you should be able to see that in time, this will be y1, this will be y2, true, as a value. And those two values tell us something like this. Very clear, not clear at all, kind of clear. Excellent. And we were discussing about equilibria. So let's say I have the same situation as before, time, y1, y2, and I see that I have something that goes constant here and something that goes down here. What are you able to tell me about those values in the y-axis? You got the point. Discuss. If you see that time frame, what can you say about the derivatives? Basic. Okay, so let's see. Madonna, and now this stuff here. I'm this one. Can we move it around? No, of course not. This one, is it positive, negative, or equal to zero? Equal to zero, true? Because we have constant. Y1 dot is equal to zero. And the second one has to be negative. Would we say that for the system, this point here is an equilibrium? Yes, it's an equilibrium. No, it's not an equilibrium. I do not know. No. Why? What is the definition of an equilibrium? All the dots have to be zero. All the dots have to be zero to be an equilibrium. So this is the main point. To be an equilibrium, it must be, think at the stick. If it is going down in this direction and not in this direction, it means that this component here is changing and this component here is not changing, true? Do you see that this would be one component that stays constant and another component that is changing? Everything has to be zero so that, as a definition that we say, the system is in equilibrium. Together? Perfect. What does it mean? Think at this function here. This function here is going to meet the xy plane somewhere. So this one is the set of all the points that somehow make y dot 1 equal to 0. And then this one might be such that this set here, this line here, is the set of y1, y2 that makes y2 dot 0. True? It means that in a certain sense, if I want to find the equilibrium of the system, I have to, let's plot it from above. If this one was the locus of zeros for y dot 1, and this one is the locus of zeros for y2, how many equilibria will I have? 1, 2, 3, 4. True? How much are we together, people? 1, 2, 3. Excellent. So, now we have an intuition about equilibrium. We are going to see something. I do a small introduction here, but we will go delve into it a little bit better later on. What is important for us? If we have a control system for which y dot, we have eventually an ODE that looks like this one, and we would like our system to stay here as a value. Is this control system a good control system? If I designed a control system such that eventually the dynamics look like those ones, is it a nice control system? Discuss. Let's see what you say. Yes, it's a nice control system. No, it's not. And I do not know. So, okay, people. As control engineers, would you be happy, sad, or you do not know what to be? You would be sad. Why? Excellent. Because if I start here, that means I pushed the system a little bit. Where will the trajectory go? In this direction, true? So we go out. We would like the plant to produce this amount, but as soon as the plant moves a little bit from the operating condition, it escapes. Something that we do not want. Okay? This is stability. We are going to do it very formally later on. Okay? So, very important thing that I really hope that we are together. Whenever I talk about this system here, y dot, what is the order of the system? Y dot? 1. It's order 1 because the maximum number of dots that I see around is 1. True? It's a first order system. Where do the trajectories of the system live? For trajectories of the system, we discuss about the dimension of this object here. This is a signal, true? Will this signal here, live along this axis, along this axis, 1, around this plane, 2, 3, you do not know. Is the question clear? I have y of t. Y of t is a quantity, true? Let's say the temperature, the average temperature of the air in this room, okay? How many dimensions does it have? 1. For every t, it's a real number, true? So for every t, is it a point along this axis or is it a point along this plane? Along the axis. Together, are we seeing? You see it? actually y dot t, y t for every t is something that lives on the plane. True? We are together on that? Perfect. So watch out. This is a common mistake that people tend to do. Okay? This is a extremely easy way for me to see if somebody has been following the course or not. Super easy. I ask to plot the trajectories of a system y dot, and I do something like this. And then I say, starting from this initial condition, where do the trajectories go? As a question. The trajectory does like this, first option. The trajectory does like this, second option. 3, this has no sense. This question has no sense. 4, I do not know. What is the answer? The answer is that this question has no sense. Because I'm saying whenever I draw this, it means that the system has order 1. If it has order 1, the initial conditions, I'm talking about y dot is equal to f of y. The initial condition is on where? The initial condition is on this side. So initial condition is a scalar. True? Are we together? How much are we together up to now? That if I have a first order system, the initial condition is on the y, not on the y dot. True? Think at a car. Acceleration is equal to blah, 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 blah. The initial conditions are on position and velocity. True? Order 2, how many initial conditions do I have? 2. Order 3, how many initial conditions will I have? 3. Indeed, I will have y3 dots equal blah, 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 and I will have initial condition on y, initial condition on y point dot, and initial condition on y2 dot. Together, the initial conditions are on the right-hand side of the ODE. Together, here, how many initial conditions did I set up? 2. Together? So here, the answer would have been, this question is badly formulated. The initial conditions have to live here. Okay? Question.
What time do you have more initial conditions?
In which sense?
So I understand that for first order, you need one initial condition to kind of determine where it goes. But does that also exclude that we can have an initial condition for the derivative?
If I have, it's excellent question. If I have this ODE, and this is 1 and this is 1, okay, 1 and 1. Can I have as initial condition y dot at time 0 equal to 1 and y at time 0 equal to 1? Yes, no, I do not know. Discuss. Is the question clear? Given this model, that is this ODE, may I have that initial condition? Okay, people, what would you say? What would you say? The answer would be no. Why? Because this is a model, true? This means that my y dot has to be connected to y with a certain rule, true? This graph here is this rule here, true? If I get a point here that doesn't satisfy the stuff here, it's not part of the model. You see? If I put the two numbers here and I put this value, let's call it star, and let's call this one square, and I put star equals to f of square, this is false. True? Are we together? So once I define the ODE, the initial conditions are on the right-hand side. And of course, here, how many initial conditions will I have? For a system like this one, how many initial conditions will I have? 2. I need to have a point. I need to have a point on in the domain. See, because whenever I have a point on the domain, it means that from a time perspective, I've got, let's call it blue and violet. I will have something looking like this. True? The initial condition will be that point. From the initial condition, I will compute derivative and derivative. That means derivative and derivative. And then I will be able to create the trajectory. How? For example, using Euler's cubes for doing this numerical integration. So, together, for making Euler start, for a kind of a, how do you say, run Euler backward, forward, whatever it is, algorithm, I need an initial condition. I need something on the right-hand side of the equations. Together? Let's make another example. If I have position to dot is equal to minus k position plus, no, minus, Andrea, I hope Andrea hears me, minus b p dot plus u. This model here, which model is it? Physically, which type of model is this one? Spring mass system. So, K is the spring, B is the friction, and P is position. How are we together on this? If you feel uncomfortable about associating this model with a mechanical counterpart, go back and study this type of stuff. For example, you ask ChatGPT, repeat me how to derive the ODEs of a spring mass system. Okay? Together, we have to be together at the exam. This type of stuff, you need to know it. Okay? They are prerequisites. Are we together, people? Perfect. The initial conditions, how will they look like? Initial position, initial velocity. Do I need initial acceleration? No, because I'm going to compute it. Stop. Perfect. Andrea, may you give me some signs that you hear me and you see me? There's the reactions. I hope. Perfect. Can hear and see. Okay, in this case here, what are the equilibria? Go, compute them. Compute the equilibria. What do we need to add? This is a plane, true? Depending on A and B, this is a plane, true? What are the equilibria? Y dot is equal to 0. Be active, be active. Right now, even if you do not know what to write something. Y dot equal to 0. Right. I know that I bother you people. Look at me. Look at the solution. Y is equal to minus b over a times u. True? Y dot is equal to 0. It means that this has to be to 0. And then what do we do? Y is equal to a certain function. True? What is this stuff here? This stuff here is something along the axis. From a geometrical perspective, what is it? the plane. If I have a plane that somehow is oriented somewhere, that one is going to be what? The intersection of the plane with the UY axis, UY plane. Do you see it, people? Do you see it? Shall I go to GeoGebra or do you see it? You see it. Perfect. And 0, 0 is going to be an equilibrium, true? Why? Well, if I put 0 here and 0 here, what do I get? Together? Together? Perfect. What does it mean whenever u is not a constant? What is u? U in our lexicon is our control input. It's basically the motor, how much I push the motor, true? And I might push the motor more and less and more or less, and I can have something that changes here, true? In time, if in time I say that u is not constant, it means that in time u does something like this, true? That means that if I think at this axis here, it's going to be something that goes up and forth, back and forth like this. Are you seeing animation? You see? Perfect. What does it mean? Can we have an equilibrium in this case? If I have u that is changing all the time, can I have y dot equal to 0 for this type of system? No, people, it has to change. It has to change, true? Do you see? If I take this stuff here and this one is changing, to have y dot equal to 0, I need to have this one that is changing. And that means that y dot cannot be 0. Explain it to the others in the table. Go, 1 minute. Explain why for this type of systems, for you that is not constant, you cannot have an equilibrium. Together, people? Together? Are we together? Perfect. How do you feel? Very much together, not at all, kind of. Everybody answers, please, people. It's very important for me to. Excellent. Are there questions? Are there questions about this? No. Let's go on. You can ask questions also later. People, don't worry. Shall we find the equilibria here? How do I find the equilibria here? You're going to do it also in the tomorrow morning. I need to have this equal to 0 and this equal to 0. How do I solve this equation here equal to 0? I will have y rabbits. That is going to be 0.4 minus 0.5 y foxes equal to 0, true? I will do something similar here. And then I will have what? A system of equations. True? Assuming that I do not have, this is actually important because from a graphical perspective, I hope that this year, last year I didn't put too much stress on this, but it's a if I start from 0, 0, it means that I have death, true? Extinction level. So another equilibrium where we have a certain number of foxes, a certain number of rabbits, in a certain sense implies that whenever I do this, I can also actually do this. I can divide by y rabbits equal to 0, true? And in the plane rabbits, foxes, no, sorry, it's actually wrong. Let me do like this. Sorry, I should have used the other one, y rabbits. Okay, so this one is the plane y rabbits and y foxes. Together? This equation here says that I will have no change in rabbits whenever the foxes are going to be 0.4 divided 0.5. That is 0.8. This is the set of points where I have the first blanket that is equal to 0. Are you seeing this? No. Let me do another one. And last year, I basically skipped it, and I think I made a mistake about skipping it. Are we together that we have y? Let's put it. No, this doesn't work. Rabbits, foxes, rabbits dot. True. And then I have a blanket. True. And then I will have the blanket that will intersect the plane. There, it's where I will have rabbit dot equal to 0. True. Whenever I set rabbits dot equal to 0, I get what? This equation here. I get, let me rewrite it. Rabbits dot equal to 0 implies y foxes equals to 0.4 divided 0.5. Are we together? Are we following it? This one is essentially this stuff here, and it's not a curve, it's actually a line. True? If I do the same for foxes dot equal to 0, look at the structure of this, I get another line. This is going to be my point of equilibrium. It's where the two curves meet. The two implicit curves meet. And for the logical Volterra, they are not curved, but they are lines. But in general, there are going to be curves, implicit curves. Do you see it? Perfect. So if I take this number here and I make it smaller, what does it imply? It implies making this one smaller, true? That implies moving this line in this direction. You see? By changing the parameters, basically you are moving those two lines. Okay? Question.
When we were describing the fact that you have the U that changed with as function of time, we cannot have equilibrium because it doesn't make sense in that equation. Why, since here we have, like for example, rabbits that is also a function of time, we can have equilibrium? What's the difference?
Because here we have the dots on both variables.
Okay.
Well, there U is a control variable.
Okay.
Here they are dynamics that are implicitly defined by the F, while the U is something that you as a human decide.
Okay.
Okay. You see? It's from a no taxonomical level that they are different type of signals. That's another question.
Yeah, you had the axis, the vertical axis was y foxes, and the horizontal was y rabbits, right?
I might have made a mess. Let's.
I thought it was should have been the other way around.
Could be. I'm a little bit faster, so I might make mistakes on labeling things. We are getting, for each equation, we get a line, and then changing the parameters, we move the lines. And then whenever the two lines meet, that is the equilibrium for both. Okay, perfect. Okay, summarizing, how do we compute the equilibrium of an ODE? We basically put F equal to 0 and compute the corresponding points. Okay? Sometimes, not always, in this course for sure, but in more advanced courses might not be the case. For example, if you have a time varying system, sometimes, for our case for sure, we will need to put u equal to constant and disturbance is equal to constant. Okay? So in those simplified settings in this course, we are going to have that equilibrium means that everything is constant. More advanced courses, you're going to have some change. Let's make an example. If I have y dot equals to minus y plus 1 over t times u, this is, how would you classify this system here? As time constant, time varying, you do not know. This is time varying, true? Do you see that by putting u equals to t, you get 0? If I put u equals to t as a signal, u equals to t, it's a ramp, true? Do you see it? I get this one that becomes 1 and goes minus, sorry, what am I saying? Y equals to 1 would be an equilibrium. You see, the solution 1t as y0 u, this would be an equilibrium. Okay, you see, for time varying systems, we might have u equals to different from constant. But in our case, we are going to work with time constant systems. We will need the u equals to constant. I'm kind of making your life a little bit more difficult right now. But I hope you get the point, and you will see that whenever we will compute examples for our systems in this course, they will have to have u and d equal to constant in time. Python code. Recap, I would say that you can check by yourself. It's what I was saying before. Let's do this one. Very easy, but I hope we are together. Go, discuss and tell me what you think. I would say that this should be very obvious. Okay, people. I think. What would you answer here? Perfect. Excellent. Okay. Other questions? No. And then let's stop. Also, in internet, in case, just in